Hello, everyone. Um, Thanks for being here today. The idea is that I wanted to introduce the first assignment of the 3D modeling course. Can you just post something in the Twitch chat so that I know that the audio is working properly and you hear me well? Um, so the idea of the thanks for posting. The idea of the assignment is that we have something like this. So this is a mesh of the model of the Faculty of Architecture, the built environment. I hope you had at least a short opportunity to be there based on the current situation. And we want to compute the volume of the two buildings. So either the about the main building of the faculty and the pub, which is here. This is triangular mesh model. So it is only composed of triangles. It's a model courtesy of Ravi from a few years ago. What is interesting about this model is that it's not really valid or manifold. So it is a sort of an easily generated model. And if you wanted to compute the volume operation directly on this mesh, it would be tricky because it might not even be a closed volume. So I haven't really checked, but there might be some small gaps or some overlapping phases. For sure, it's not a manifold. So doing computations on this kind of mesh is quite difficult. And the idea is that in order to compute the volume of this building, you will have to voxelize it in 2 steps. So here we can see a voxelized model. I shrunk the cubes a little bit here so that you can actually see the interior of the building. If you can, if you pay a bit of attention here, you can see that the model is actually empty. So we're following the voxelization method that is in the handout of this lesson, lesson 2.1. And if you go inside the building, you will notice that only the voxels that are intersecting the boundary of the mesh that we showed previously are actually being voxelized. But in order to compute the volume, you will also have to fill the model. So you go from that to something like this, which contains actually voxels also in the interior. Yeah, there are a few steps that you need to do to achieve this. So everything is available on the course website in the homework page. So let's go through this a bit quickly. The original model of the faculty is an OBJ file. In case you haven't seen one before, they look something like this. So it's a simple ASCII plain text file. You have a series of vertices. Each vertex is marked with a B at the very beginning. And then you have the X, Y, and Z coordinates separated by a space. And you just have this long list of vertices. And if you go down at some point, you start having the faces that are marked here as F. So you have like, this is the very first one. So that would be phase 1, 2, 3. This refers to vertices in the first part of the list. So 1, 2, 3 means that it's the first vertex, second vertex, and third vertex forming the face. In theory, in OBJ files, you can also have not triangular faces, but any kind of polygon. But in practice, you will see that a lot of software doesn't really support them. So it's better to always read and write only triangles, so faces with 3 vertices like these ones. You will also see some markers with a O at the beginning and then a number, or could also be text, I think. These mark separate objects in the mesh, but we are not really dealing with them here. Yeah, so you have this triangular mesh of the faculty buildings from the OBJ file, and you have to voxelize and fill it in a few steps. I have suggested a few different steps here in the homework page, but you're free to use them or to follow a different path. It's up to you. Yes, you're allowed to work in a group of 2 for this assignment, but if you prefer to work on your own, that's also fine. I personally think that it's better if you pair up with someone, because with the discussion you will actually achieve a better result, and I think you will learn more. Before the pandemic, we had the course lab, and I would be there in person, and there was also the Geo lab. And there you would be able to talk with your classmates about how things were going. Since this is not really possible in the pandemic, I decided to experiment a bit here. And I came up with the idea that it would be nice if you talk to another group about your progress. So this is sort of a mandatory part of doing the assignments. At some point during the progress of your work, you should agree to meet with a different group. If you can organize that through the Discord text channel, maybe. Yeah, just show what you're doing, like what method are you following, what are your results so far, and try to provide some feedback to the other group. Yeah, so what are you doing differently? Maybe discuss a bit like the pros and cons, which approach might work better for some cases, or what is faster, more efficient. If you download this file, the homework one zip file, you will see a few different things. First of all, there's the OBJ file that I showed you. So this is just the model of the faculty. And there inside you will also see a folder titled voxelizer. And here I gave you some snippets of code that might be useful for you. You are free to use them or to not use them if you prefer. There's a point structure that you can use to represent 3D points or 3D vectors. I added a few simple like linear algebra, some vector operations like addition of 2 vectors, subtraction of 2 vectors, multiplication and division with a scalar, dot product and cross product, plus an operator to output things like using a standard output like cout. You will also have a similar structure like this one for rows. So the one for points used the floating point coordinates to represent the 3D points. This one for the rows has like integer coordinates so that you can represent like the rows in the voxel grid. So the row along the x-axis, the y-axis, and the z-axis, plus a few simple operations. This structure for the actual voxel grid, so you can initialize it with the size. So you just say like I want a grid of x by y by z voxels, and yeah, you can access the voxels just also by x, y, and z coordinates from the rows that you have defined previously. These 3 files are exactly as I used them to generate the code, and I also included the main file that I used to solve the homework assignment, but of course I removed the important bits. So but maybe it gives you a bit of structure on how to get things done. So there's like function to compute the sine volume that we will discuss in a bit, the intersection, and more or less the steps that are detailed in the homework page. So going back to the homework page, I discussed a bit how to compute this line with a triangle, this line segment triangle intersections that you need to compute. This is the key part of the algorithm that we saw in the handout, in case you have seen it already. The main idea, let's go through it in case you haven't seen it yet. Let me switch to the tablet here. Okay, so we have something like this. So we have a voxel. So this is just one voxel inside the big voxel grid. And inside each voxel, we will define 3 different targets. This is for 26 connectivity. So we define a target going from the midpoint at the top to the midpoint at the bottom. Let's maybe draw. So this is one target. There's another one that goes from here to here. Another one that goes from back to the front face, like this. And so if you have any sort of triangle, and we can imagine that the triangles are very much bigger than the voxels, you have like a big intersection with a triangle, and you simply need to test for every voxel whether any of these 3 lines, 3 line segments intersect the triangle. The idea is to do it a bit of brute force in this sense. So for every triangle in the mesh, you test every voxel more or less with these 3 line segments, which are the intersection targets. And if any of these 3 intersect the triangle, then you know that that voxel should be filled because it is intersecting the triangle. So if we start from these intersection operation, so we have narrowed down the voxelization process to intersections between line segments and triangles. There are different ways to do this. So if you Google, you will find many, but the one that I recommended is described in the homework page. So you have something like this. You have a triangle. I will draw it smaller because then it's clearer for the explanation, but the triangles will generally be much bigger than the line segments. And you will have a line, so something like this. And we can imagine that the line in this case is intersecting the triangle. So we have an operation called the sine volume, and the sine volume is that given tetrahedron. So we have something like this for a tetrahedron. The sine volume, if you give the vertices A, B, C, and D in this order. Sorry, let me move this a bit down. So if you give the vertices in this order, A, B, C, and D, you follow the right-hand rule. And D, if D is on the positive side of the plane, you will get a positive volume. If D is on the negative side of the plane, so D is here, you will get a negative volume. If you are not familiar with this, yeah, so basically you have 3 vertices, and you use your index finger so to follow them in order, like A, B, C, and they create like an order rotating. If your thumb points towards the 4th vertex, that means that it's in the positive direction, and if it points in the opposite direction of your thumb, it means that it's in the negative direction, so on the negative side of the plane. And based on that, you define the sine volume. So the volume will be either positive or negative. Yeah, if you have questions about this, there's a link in the homework page, and otherwise just ask, no problem. So we have this operation for the sine volume, and we use the 3 vertices of the triangle. Let's say, well, the order doesn't really matter, but it can be a bit consistent. So first of all, you start with the triangle and the line segment, and you check if the 2 vertices, like in this case D and E, are on opposite sides of the triangle. So if this is the order and the order is arbitrary, you don't need to worry. One vertex of the line segment should be on one side of the triangle, and the other should be on the opposite side. So if this gives you a positive direction, this should give you a negative direction. This tells you basically the 2 endpoints of the line segment are on opposite sides of the triangle. So this is the first test that you need to do. The second one is a little bit trickier, but if we have the same thing, so the triangle and the line segment that in this case is intersecting the triangle, you basically need to check that given two vertices of the triangle. So let's define something like this. So I hope you can see a triangle here that is formed with the start and end of the line segment plus the vertex A. And the idea is that this triangle, so A start and end, creates a plane also, and this plane will intersect the triangle. So you can imagine that there's a sort of a big plane like this, and it intersects the triangle along this specific line. And you will have to test if the 2 other vertices of the triangle, the line segment refers to the target, which is not an edge of the voxel, it's one of the sort of intermediate parts. So what we discussed, the line, it's one of the 3 line segments defined like this. So they're not the edges of the voxel, they are the 3 sort of line segment that go from the middle of the top to the middle of the bottom, the middle of the left to the middle of the right, the middle of the front to the middle of the back. So those are the lines, and they correspond to this line that you're intersecting with the triangle. Yeah, so going back to this, so we have the triangle defined by 1 vertex and the 2 endpoints of the triangle. This triangle defines a plane, which we are showing here. This plane intersects the triangle along a given line. I know that this is a little bit convoluted, but then from this line, the 2 other vertices of the triangle should be on opposite sides. So if we use what we defined as the sine volume, so let's say that we give this orientation to the triangle, A start end, then this would be the positive side and this would be the negative side. So C should be on the positive side and B should be on the negative side. So you do this test to ensure that starting from 1 vertex plus the 2 vertices of the line segment, the 2 other vertices of the triangle are on opposite sides of the plane. This tells you that the line segment is actually falling inside the triangle, because with the test that we previously did, we could have a case like this where the one endpoint of the line segment was clearly on the top, one endpoint of the line segment was clearly on the bottom, but the line segment was not crossing the triangle at all, so it was sort of on one side. And we want to test that the line segment is actually falling on the triangle. So we need to do the other test, and the idea is that you will do it for all three vertices. So first you use this triangle with A, start and end, but then you will do the same thing using B, start and end, and then you will do the same thing with C, start and end. And you test whether the other two vertices of the triangle lie on opposite sides of the plane that you generate through this, which you check by doing the sine volume and making sure that the sine volume has different signs for the two other vertices. I think this is clear once you start programming it, but in case anything goes wrong, just ask a question in the text channel or let me know and we can go through it. So going back to the homework page, you implement this and you will do a maximum of 4 or 5 tests depending on how you choose to implement this. I think usually you would get 4 different tests. So one for the check here on the left, making sure that the origin and destination are on opposite sides of the triangle, and then 3 for the 3 vertices with the triangle, so making sure that given one vertex, the other 2 are on opposite sides, and you do this for every vertex. So that would be usually 4 different tests. But you can imagine that this is pretty much brute force. So for every voxel, we have 3 line segments, and you might want to do this for every single voxel in the model, for every single triangle in the model. This can be quite slow. And I am proposing to you to use a very simple optimization here. That is to use a bounding box of the original triangle. So if we go back to this, the idea is that if you start from a given triangle in 3D space, you can sort of find a bounding box for it. So you find the minimum and maximum coordinates on the X, Y, and Z direction, and this will give you sort of a box where it fits. Let's say that this is on the plane and this is on the top, and only the voxels that are partly within this bounding box of the triangle. By partly I mean that there might be some voxels that are, touching the bounding box. So part of the bounding box is inside the voxel, part of it is outside, and you only need to do this computation of the intersections for the voxels that are either fully within the bounding box or partly within the bounding box. This will greatly reduce the computation that you need to do, because the triangles are pretty small compared to the full model. So usually the bounding box of a given triangle will give you, I don't know, like 50 or 100 voxels rather than tens of thousands or hundreds of thousands of voxels. And this is a pretty easy optimization to make, so I'm really recommending you to do it. Maybe not at the very beginning, but once you get the code partially working, you can add this to make it faster. So this method from the handout will give you the voxels that are intersecting the boundary of the triangular mesh of the model. And then the next step is to fill the interior of this model. So this is actually quite easy. So the idea is that you can start from one voxel that you know is in the exterior. How you do that is up to you. You can either define one specific voxel just hard-coded that you know is outside, or maybe start from a corner of the voxel grid, like a top corner. And since in the Faculty of Architecture there's only this, this tall tower that is not really in a corner, you know that a corner of the voxel grid will be empty, and then from this voxel that you know is empty, you can sort of flood all of the voxels that are touching it, like recursively, so that you mark all of these voxels as exterior, use a specific value, like I think in my code I use the value 2 to mark the exterior, and then everything that stays with the original empty value, which in my case was 0, is in the interior of the two buildings. This works because we know that the voxels are sort of completely surrounding some spaces, and the exterior of the models is totally connected. So if you start from one voxel that you know is outside and you sort of flood from there, you will get every single voxel from the exterior. So what you get at the end is the interior of two buildings. I'm giving you some tips for this. So what I used for debugging was just writing another OBJ file, the one that I showed you at the beginning. This OBJ file just has like a voxelized version of the model. I would recommend that you shrink the voxels a little bit, because otherwise the two voxels that are adjacent will have overlapping faces, and you generally want to avoid that. Plus, it allows you to see easily whether the stuff that you have in the interior of the model is fine or not. There are two pieces of software that might be useful. I think MeshLab in general is nice for debugging because it's pretty quick and easy, and it directly zooms into the voxel model that you generate as an OBJ file. And if you want to generate nice figures for your report, which you have to do a report, Blender is a nice tool to do it. If you look at this thing that I added in the beginning of the page, this is actually generated using Blender. Yes, for the volume calculation, there are a few things. Some voxels will be fully inside the model, some voxels will be fully outside the building, some will be on the boundary. If you counted, you will compute the volume of the building just by counting voxels, because every voxel has a fixed size. That's one of the benefits of voxels. But if you counted the boundary voxels as being fully inside the building, you will be overestimating the volume, right? So the quick and easy way to get an approximate volume for the building would be to count the interior voxels as 1, the exterior voxels as 0, and the boundary voxels as 0.5, so half a voxel. In that way, you assume that in a boundary voxel, sort of half of it is inside and half of it is outside the building, and with the small enough voxels, this will give you a good approximation of the volume. So the deliverables, you need to submit your code. It should work. You need to submit a report where you document how you did things. The idea is to just have a very simple, short report that I can go through, and a voxelized version of the model produced by your code. So mostly I will not look very much at your code. I will use it as reference to check for things in case things are not clear in the report. But mostly I will just look at the voxelized version of the model that you submit and the report, plus test that your code is actually working. So for the code, you should submit all the files that are part of it. It should output the final volume of the model. and it should output the voxelized version of the model as an OBJ file similar to the one that you get as input. Everything should be implemented in C++ using libraries from the C++ standard library. So yeah, anything from the STL that you get is fine. So that includes like all the data structures, like vectors, lists, stacks, all the algorithms that are there in like algorithm.h, or like the assertions that I added, and I think yeah, one of you already saw that you might need to add a header to make those compile properly. So anything that's in the C++ standard library is fine. So no boost, no seagull, no stuff that solves the problem for you, please. The report is really a simple report. Just say what you're doing, why are you doing it that way. Just briefly document the key parts of the algorithm. You don't need to go through your code line by line. In fact, please don't go through your code line by line. Just tell me what are the key steps, more or less, what is your strategy to tackle the problem, and include a short discussion. So give me the pros and cons of your method. Like, it's okay if your code doesn't work flawlessly. Just honestly document that this works well and that doesn't work so well. Assess the quality, like look at your final voxel model and see if it's good or not. If you see some problems, just document them in the report. And the performance, so how long it takes, using differently sized voxels. So try to see if it would scale to, let's say, a model of the whole city of Delft or the whole country of the Netherlands. Maybe would this be feasible or not based on the performance of your code? Yeah, since we had this sort of structured peer review with the other group, please use a small section of the report to say how the other group was doing whenever you met. You are free to meet them whenever you want, like it can be at the beginning or at the very end. My recommendation would be more somewhere in the middle, so that you can actually have some time to process the feedback and maybe to change what you're doing in case you figure out that what you're doing is not ideal. Focus on what they're doing differently, so differently from what your own group is doing. It's meant to be a maximum of 5 pages for the report, so it's really a short report. Shorter the better. Just make sure that you say what you're doing. Yeah, don't forget to write your names and the names of the other group. For the voxelized model, my recommendation is to use that the one that you submit is to submit it using 1 meter voxels or smaller. I think 1 meter voxels are more than fine enough. Otherwise, the models will be huge. But for the calculation, in general, the smaller the voxels, the more accurate your calculation will be. So once you get your code working properly, maybe use small voxels and leave it running overnight, and you will get a much better calculation that you would get otherwise. Yeah, so it will be marked in this way. I will just make sure that I will just compile your code and run it. If it compiles and runs properly without modifications, I will give you a point. In case there are small compilation issues like headers and so on, I will not deduct points based on that. Just make sure that it works on your computer and you will get the point. If the code outputs the voxelized and filled model, you will get 3 points. If it computes the correct volume, let's say plus or minus something like 10%, then you will get 2 points. 3 points will be based on the report, so try to write a nice report. It's a short one. Just be very clear about what you do. It doesn't have to be pretty, just professional, clear report. And 1 point, which is sort of a freebie for discussing with another group, so just try to do it. It's just a quick way to encourage you to actually do the peer review. And there's a Dropbox link that you can use to submit everything here. Yeah, I think in the DTM course, a lot of you prefer Dropbox because it gives you like an email showing that you actually submitted the file. Yeah, so that's basically it. I will be around for the full 2 hours and likely longer to answer any questions you might have about handouts or about the assignment. If you're completely lost, it's okay. Just send me a message, either a DM or post something in the text channel of the course, and we can go through it and solve any doubts you might have. Or if you are completely lost, at least gives you point you in the right direction to get started. So thanks to you all for being here, and I'll see you all online. Bye.